Everybody here in person and on Zoom. My name is Ani Sidrizis, for those of you who don't know me, and I'm a third-year PhD student at the Institute of Optics, working with Professors René Corolin and Michele Brucci. Thank you for joining us for Voices of XR, a Marianne Maverick Studio X speaker series. This series is made possible by Kathy McMahon-Murray and the National Science Foundation as a part of the interdisciplinary graduate training in science, technology, and application of augmented and virtual reality here at the University of Rochester. It is my special pleasure to introduce our speaker today, Nihar Mohanty, who joins us from Meta. He works with the near eye display technology at Meta, where he is an optical integration scientist. Nihar leads a team of world-class research scientists and engineers toward the development of an all-day wearable augmented reality display. His specialties are in augmented reality, displays, waveguides, diffractive optics, patterning integration, materials development, plasma etch, project management, graphene devices, and graphene sensors. Please feel free to post any questions you may have in the chat, and we will have a Q&A later. Lastly, this session is being recorded and will be available to you later on the Studio X website. And with that, I give the floor to our speaker, Nihar. The floor is yours.
Thank you. Thanks for the kind introduction. So excited to speak at the University of Rochester Voices of XR. So thanks for the invitation and thanks for reminding me because I had completely forgotten about this. So as you are seeing, so I'm Nihar Mohanty and I'm an R&D manager at the Meta Reality Labs, and I work on advanced augmented reality displays. And as a lifelong wearer of prescription glasses, I think I remember I started wearing prescription glasses when I was probably second grade or, second grade, I remember. I consider myself to have a side gig of modeling our AR glasses. I love trying out AR glasses. And in this picture, you can see me truly sporting our truly immersive AR glasses that we codenamed Orion, that looks just like a pair of sunglasses. This is the sunglass version. Of course, I'm not showing here the regular glass version that is fully transparent. Today, I'm going to give you a peek behind the curtain on our long-standing work towards enabling Orion. So this is work that we completed in research almost 3 years back. So for the first time, so this is the second time after the Photonics West that I'm giving this talk, where I'm going to talk to you about all the things that went into making this Orion. Orion is truly a technological marvel, and the full story of the full glasses might need a full day. Hence, today I will be focusing on one small part of Orion. Let me see if my cursor is working. Okay, so which is the waveguide. And if you are familiar with near-eye displays, waveguide is the core and the most critical component of the display system. And for Orion, we chose the SRG waveguide, and that's what I'm going to focus today more on. Okay, so recently one of my favorite movie directors, James Cameron, visited our CTO, and he got to see some of our research in the Reality Labs before announcing a multi-year partnership, which you can read more about in the press release. One fun fact about James Cameron is that he's big into the deep sea submersibles and into exploring the enormous depths of our oceans. He was one of the first people to dive down to the depths of over 12,000 feet to explore the Titanic wreckage, which even to this day remains a mystery. However, considering that the oceans cover about 2/3 of the Earth's surface area, there haven't been many more events like this. And James Cameron, he recently visited, had a fireside chat with our CTO where he talked about how areas as big as the continental United States are yet to be explored in the oceans. That might have given rise to the saying that we know more about space than our oceans, which are right next to us. And one of the key reasons for this is that the submersibles have been stuck in the old times. With the super tiny portholes where you can barely see anything, the enigma to the deep sea exploration just wasn't there outside of the military. As visual creatures, we deeply care about being able to see things with our own eyes when doing activities which no amount of digital recreation can replace. And of course, this wasn't due to the lack of trying, it was due to the limitations of the materials and processes at that time. The times have changed now. Recent advances in material science and manufacturing processes, such as with high-strength acrylics and carbon fiber load-bearing structures, have enabled a new class of deep-sea submersibles that enable panoramic views instead of the old-school vehicles. This has led to a surge in interest from the general public, with the market set to grow more than 5x in the next 5 years. This, in a completely different area that we work on, is a testament to how important visual stimuli is for us as humans and has parallels in many, many different areas. So, of course, not all of us are as artistic or as adventurous or, importantly, as rich as James Cameron. But we do like watching his exploits from the comfort of our home on our television sets. If you plot the average size of the TV sets over the last 2 decades, the trend is obvious on the move towards larger and larger display sizes with no sign of a slowdown. This has been irrespective of any display panel technology, be it LCD, be it OLED, or even the micro LED panels. Now you can see where I'm going. There is a common theme here. It's the field of view. We want large field of view anywhere and everywhere where there is any visual stimuli involved. We build houses with floor-to-ceiling windows. We build cars with panoramic windows and panoramic roofs. And even the good old smartphone that has the biggest limit of being able to fit inside our pockets is moving into foldable screens to allow you to have a large screen. I would argue that large field of view is not just a want, it is a need that has been shaped by the forces of evolution. Even if we lack resolution in our peripheral vision, we are sensitive to temporal stimulus, such as movement, which, when impeded, makes us uncomfortable. This is a consequence of evolutionary pressure that had material impact on our survival. As when in this image that I generated in Gemini, when early men were hunting for food, they were being hunted, and having that peripheral vision outside of your central gaze was critical and was a matter of life or death for you. Now, fast forward a few 100,000 years, and this still holds in our modern world. There have been numerous studies on the importance of peripheral vision on the modern day-to-day life and its impact on the cognitive load. Augmented reality glasses, which enhance our real-world vision, which enhance our real world with visual informational cues, need to have large field of view covering the peripheral vision to reduce the cognitive load in our daily life, as well as to bring a sense of being the natural part of the environment. You can experience this for yourself by trying a small field of view AR display, followed by the same with an equivalent large field of view display. And you will discover your preference for the large field of view display, even if you cannot articulate exactly why, and even if the use case might be exactly the same. Even if you disagree with all the science, and if you take a typical laptop at arm's length, it subtends an angle of about 35 cross 25 degrees. It's obvious that your AR glass display needs to be much bigger in order to augment and not intrude upon your activity. Now that I have convinced you for the need for the large field of view for AR, the question arises on what should the dimensions of this large field of view be? How large is large field of view? For this, we have to get back to the fundamentals of the human visual system. The typical human visual system covers about 150 degrees horizontal and greater than 100 degrees in vertical for each eye, with the shape bounded by the occlusion from the nose. This results in an overlapped area for both eyes that we call the binocular overlap region. That's about 140 degrees roughly, give or take, for horizontal, and also 100 degrees in vertical, which is a much narrower shape. While covering the full human vision would be an aspirational goal, one way to bring realism into the picture is to look at what are the binocular vision limits as bounded by typical prescription glasses, as they are the avenue by which we can enable augmented reality. Modern versions of the prescription glasses have been around since 1300 AD. On the right here, you can see the extent of the full human vision that is supported by glasses for vision correction, the prescription glasses. For AR glasses, this limits the binocular display field of view to about 70 cross 70 as shown by the dotted square. This defines how large a large field of view display can be in implementation as with a prescription glass. A good start for truly immersive large field of view augmented reality display is for greater than 70-degree diagonal displays. And this translates to about a 120-inch TV, about 8 feet away. Before I go deep into the Orion's background, I wanted to give a brief preview of the typical pupil replication displays for a surface relief grating based waveguide combiners. The system integration is pretty simple. You start with a really small emissive display that you can fit in the glasses. In this example, this is a tiny micro LED based display. You add a collimating lens for virtual image formation. Now you add a waveguide, which is a transparent piece of glass with diffractive structures that are called surface relief gratings that modulate the light. These are sub-wavelength structures. The glass typically has separate input and output couplers in spatially separate structures. Now, when the light hits the combiner, the input coupler, it gets diffracted and gets trapped inside the glass due to total internal reflection condition and keeps bouncing back and forth between the two surfaces of the glass and hitting the output multiple times. The output diffracts the light in such a way that the total internal reflection condition is not met and the light can escape from the glass. This method replicates the input pupil from the micro display all along the output coupling, which can be optimized to have the brightest efficiency, brightest extraction, the most extraction in a two-dimensional area on the waveguide or a three-dimensional area for your eyes called the eye box. This is one of the most common methods for creating an AR display, and this is Orion's principle of how we made the AR display with surface relief grating. That would be the focus of this talk. Large field of view AR displays are not new. There have been multiple displays that have been pushing the field of view over the last 5 years. The AR display roadmap started with the HoloLens 1 with a 35-degree diagonal display with three glass plates. Then came the Magic Leap 1 with a 50-degree diagonal display with three glass plates per plane and two planes, so a total of 6 planes. Then came HoloLens 2 with a 52-degree diagonal display with 2 plates of glass. And recently, Snap came up with a 46-degree diagonal with assumed 2 plates. The largest display that has been demonstrated, augmented reality display that has been demonstrated in public, has been the Magic Leap 2 with a 70-degree diagonal display in portrait mode using 3-plate glass waveguides. So you would ask, is the problem solved? There is a but. Field of view is key, but it's not the only thing that matters for immersive AR glasses. All augmented reality displays are additive displays, which means they show content by adding light to the real-world background. This means that the display quality as quantified by brightness, which translates to the efficiency of the waveguide, and color uniformity at high resolution, which translates to waveguide MTF, is critical. If we are to use the immersive AR glasses indoors and outdoors, we need the display to be bright enough to have high ambient contrast ratio with respect to the surroundings. As an example, even in the indoors, we have a variety of lighting conditions going from about 100 to 200 nits of background to living rooms with 300 to 500 in the living rooms to about 300 and 500 nits in the bright kitchen. A back of the envelope calculation for achieving a CR of 5 indoors needs about 500 to 2500 nits of display brightness. And of course, for the ultimate goal for AR display is to eventually achieve the retinal resolution, which is about 1 arc minute. The key area that has been totally an afterthought for most large field of view products in the market is the rainbow and form factor. And with form factor comes the weight. For AR glasses to be all-day wearable, reducing the rainbow artifacts, which is the key flaw of surface relief grating waveguides, is important without compromising on form factor and weight, as these glasses are truly a fashionable medical accessory. This is where all the products in the market have struggled. All it takes for you to be obsessed with rainbow is seeing it once. All large field of view waveguides in the market have high rainbow indoors and outdoors and have a large form factor with system weight close to half a pound to 2 pounds. For reference, the typical prescription glasses are 15 to 30 grams. The ones that I'm wearing right now are about 31 grams. Here is a typical two-plate glass-based large field of view waveguide in the left in the center images, where you can see the rainbow in your field of view, both outdoors. This is an outdoor image. And then indoors. It is hard to capture how distracting the rainbow is from the video or the images. You have to experience them firsthand to see the annoying nature of this rainbow. Solving the rainbow at the small factor was the priority for us during the Orion days. To solve the rainbow problem, you first need to understand the problem space. For typical SRG waveguides, the rainbow originates from unwanted diffraction of the azimuthal light sources, such as the ceiling lights indoors or the sun outdoors, or even from the light of the cars that are behind you while you are driving in the night. When the light sources are in the front, there could be two main paths for the rainbow formation, where the rainbow intensity is high enough to be visible to the eye. The one where it diffracts once from the gratings, or the second where it could diffract twice after bouncing back and forth in the glass plate. In the case when the light source is on the back of the glasses, the single diffraction case is the one that produces visible rainbow intensity. All the other interactions have low enough intensity to be invisible. However, when there are multiple plates, there is a combination of many paths that reaches to your eye, both from the front side and the back side. And increase this to more plates, let's say 3 plates, the rainbow goes up significantly. Now that you have seen the mechanisms, I'll walk you through our solution space. The first step was obvious, which is reduce the complexity of the problem and to have just one plate for the waveguide. This is not a trivial problem because we did not want to compromise on the field of view. The max field of view that is supported by a waveguide is determined by the refractive index of the waveguide substrate. The actual field of view that is achieved is further clipped by the surface relief grating, SRG grating designs. You can see from the table on the left here, various substrate types, the refractive index, and the max extents of the theoretical field of view that they can support. To truly appreciate this field of view, you need to look at the max field of view supported with respect to the full human binocular vision. It is clear here that silicon carbide, with its refractive index close to 2.6, is the choice. And the best part, it has much lower density, making it one of the lightest options. So call that two birds with the same stone. Now, when you plot the max field of view allowed by the silicon carbide overlaid with the limits of the display field of view as defined by typical prescription glass frames, you can see that it is almost approaching the max limits. It is important to note that the actual white field of view is smaller at the corners due to the dispersive nature of the SRG gratings, which is determined by the intersection of the red, green, and blue field of views. However, if you allow some perceptually acceptable amount of binocular fusion, we can get pretty close to the max extents with silicon carbide. Now that you have a single plate waveguide, The second key path to reduce the rainbow is to reduce the rainbow intensity. The key challenge here is to reduce the rainbow while not impacting the display path, as they both share similar paths. Analogous to the principles of active noise cancelling, whereby using a destructive interference between two signals, the noise signal can be cancelled, we discovered similar phenomena with deep gratings at 45 to 60 degree slant, which at optimum thickness can reduce some of the rainbow paths through destructive interference with minimal impact on the display path. Underline, I said some of the rainbow paths. This only works for the front side rainbow. There are two key aspects to this approach. The depth and slant angle of the gratings needs to be within the optimum range, not too deep, not too shallow. And the anti-reflective coating needs to be at broadband at wide angles ranging from plus minus 90 degrees. This architecture is so efficient in reducing the rainbow that with optimized unit cell architecture, unit cell for the gratings, the front rainbow for even the glass devices is significantly suppressed, as you can see in the image. The grating slant in the unit cell on the bottom shown was up to 65 degrees with high index grating layers and low index grating immersion layers that we called overcoats with a moth-eye arc on the top. We believe this to be one of the most sophisticated sRG grating-based waveguide in the industry. If you have caught my theme here, there is a but coming. The brightness of the light sources in our daily life varies a lot. In the indoors, you could have light sources that are a few thousand to a few million nits. Outside, the problem is even bigger. The sun in a cloudless day, as we have today in Seattle, could be a billion nits. So even if you have low rainbow efficiency, let's say about 0.1%, the rainbow intensity is staggering with bright sources. This tells us that reducing the rainbow intensity for an all-day wearable device is not enough. And this is where we had our final path. This starts with a simple premise, which is to eliminate the rainbow paths to the eye box. One way to achieve this is with smaller pitch gratings, which pushes the diffraction angles of the light to steeper angles and hence misses the eye box. While arbitrarily smaller pitch could technically eliminate all rainbow paths to the eye box, it is not practical due to the need to maintain high display path efficiencies. The typical optimized pitch for silicon carbide based on single plate waveguide cuts most of the red and green paths with some faint blue paths remaining. This is an optimum scenario because our retinal receptors, they have much lower detection efficacy for blue light. Now that we identified the paths to reduce the rainbow, the next big challenge was the form factor. We wanted to make all-day wearable glasses, which means the premium on the real estate in front of your eyes was critical. There are two types of sRG grating architectures that can support temple-mounted miniature light sources: folded architectures and butterfly architectures. While the folded architecture is simpler and can be fabricated on a single side of a substrate, which is great for manufacturability, it is limited by efficiency, field of view coverage, and the desired form factor. Butterfly architecture, on the other hand, is much more complex, typically needs double-sided processing, but gives much wider design latitude for higher efficiency and field of view coverage at a much smaller form factor. We chose Butterfly as our architecture of choice on silicon carbide to maximize the performance with a small footprint. The optimized high-performance grating design architecture for Orion had split 3 red, green, and blue input couplers and discrete out couplers on each side with a slant angle for each grating optimized for performance and ranging from binary at 0 degree slant to 60 degree slanted gratings. The grating unit cell was comprised of a high index grating that is index matched with silicon carbide with an encapsulation layer, followed by the grating immersion layer that I explained before called the overcoat, and being topped off by a simpler anti-reflective coating, single layer anti-reflective coating. While this unit cell might seem daunting, it was critical to enable the high performance of Orion. Typical fabrication strategies for SRG waveguides that are common in the industry is either through nanoimprint or through traditional semiconductor-style etched paths. Both paths have their advantages and disadvantages that have been extensively covered in various conferences and review papers. Due to the very high index requirement for our gratings and the need for a variety of slant angles, including the steep 60-degree slant, we chose the etch strategy. Unlike glass or lithium niobate, where you need a functional film to etch into to create gratings, as the bulk substrate cannot be etched, in case of silicon carbide, the bulk etch is the preferred path, enabling natively index-matched gratings on silicon carbide. We followed a standard semiconductor-style fabrication flow that is similar to a far back-end of line logic metal layers with films, lithography, etch, and encapsulation blocks. For people who are not from the semiconductor industry, a typical, let's say, iPhone chip has about 12 of those metal layers in each chip. There were multiple new inventions in our path to make the silicon carbide, with over 30 patents that have been granted and several more still in processing. I picked 5 of the key innovations for you to appreciate the nature of the challenges we faced and how we solved them. In our industry, every company has their own proprietary waveguide simulation and optimization tool. The first key invention for us was fast and accurate optimization pipeline. A lot of work went into building up ours and making the simulations as close as possible to the ground truth, and also scaling that infrastructure. Key innovations that went into taking the simulation accuracy to next level was realistic grating simulations, which enables us to simulate exact features we get on the waveguide versus the traditional approach where people typically approximate a trapezoid. The next key innovation was a coherent simulation pipeline that is fast and accurate as validated by ground truth. This was the major contributor in improving our simulation accuracy, as this reflects real physics in spite of being more computationally expensive. But being part of Meta, whose family of apps include Facebook, Instagram, and WhatsApp, where people upload a billion videos every hour, this is truly our cup of tea. The next major invention was working with our partners to achieve optical grade silicon carbide. For an AR display substrate, 2 parameters are key: absorption and total thickness variation, called TTV. Typical silicon carbide grade that is common in the industry is a N-type silicon carbide, which has a greenish hue with obviously high absorption, invisible, and absolutely not suitable for AR display. Why is that? It's because for a typical SRG-based people replication waveguide, the light travels long distances. In this simple example, you can see the light travels really long distance from the input all the way into the eye box before it gets outcoupled. So even small amounts of absorption losses just saps the energy. Typical distance that visible light travels in a silicon carbide waveguide is measured in centimeters before it gets to your eye. Over the years, significant process and tool development in collaboration with our partners has enabled us to reduce the absorption by 30 times to almost negligible amounts for visible wavelengths. And you can see the results in an optical grade silicon carbide on the right here. The second key vector for improvement was enabling the optical grade silicon carbide was the flatness improvement, the TTV improvement. Once again, due to the long travel distance of the rays inside the waveguide, the flatness as defined as the TTV is critical to maintain the high resolution of the display. When we started the project, the TTV of the silicon carbide substrates was over 4 microns, which might seem pretty low for the semiconductor industry, which is the primary user of silicon carbide, but produces unacceptable display artifacts when used as display waveguides. This was especially a hard challenge, considering the hardness of silicon carbide, as defined by the Moore hardness, is just below diamond, which is the hardest material on the earth. New polishing techniques had to be developed that enabled us to reduce down the TTP of silicon carbide by 30-fold for enabling optical grade substrates. And it is obvious that diamond was used actually to polish the silicon carbide substrates. Now, the third key invention is anisotropic gratings and enabling high index slant edge. Anisotropic gratings have been well known for their ability to enable asymmetric diffraction efficiencies, which play a crucial role in achieving high performance waveguides. Ion beam etch tools are the key into achieving asymmetric gratings at volume. A typical ion beam etch system comprises of a plasma generating chamber from which ions are extracted, accelerated, and neutralized before hitting the substrate at the desired angle to create the desired slant. When we started working on etched waveguides, the hardware that was available in the market wasn't good enough to produce slanted gratings at these various slant angles with different materials. The typical hardware available at that time either enabled the reactive ion beam etch, where all your chemistry is inside the plasma chamber, or chemical assisted ion beam etch, where all your chemistry is in a gas ring that is in front of your substrate. We worked with our tooling partners to co-develop novel hardware and processes that enabled us chemically assisted reactive ion beam etch to enable multiple different types of grating unit cells, starting all the way from binary to blazed to over 60-degree slant, with a high degree of symmetricity, which has significant impact on the final optical performance. Further, this also enabled us to create slanted gratings on various kinds of materials with different refractive indices, such as silicon oxide at 1.46 or silicon nitride at 2.0 or titanium oxide at 2.5 refractive index and bulk silicon carbide at 2.6 refractive index, which at the time of publication was one of the world's first demonstrators. The fourth key technology component that we developed was the ability to achieve continuous modulation of grating depths, which we call continuously variable etch depth. To give you a little bit of background on why is that important, let's consider the simple case of a people replication-based SRG waveguide. So you can see here where the light travels from the input grating, gets expanded by the expansion grating, and is being outcoupled by the output grating in the eye box. It is obvious that inside the eye box, moving from the left to right, the grating efficiency needs to be lowest on the left and highest on the right. If the grating efficiency is too high on the left, you would extract all the light out before even the light reaches the end of the eye box. Some of the ways to achieve this modulation in grating efficiency is through the fill factor or the duty cycle, changing the duty cycle, and changing the depth. While changing the duty cycle, that we call variable duty cycle, is trivial considering the decades of advancements in lithography in the semiconductor industry, continuously variable etch depth is a major challenge to achieve at scale. A fast and scalable method to create continuously variable etch depth is to use a lithographic process in conjunction with etch, where you have a variable thickness resist called the gratone resist, and when you etch, you expose different areas of the gratings at different times. But herein lies the problem. Over the past several decades, the semiconductor industry has been developing resists that have a step function response for the dose, which is to improve the line edge roughness or the edge placement errors, because these resists are used to make lines and spaces. What we needed for our gratone resist for creating this continuously variable etch depth is a shallow and linear dose response, which is completely antagonistic to the decades of R&D for semiconductors. We had to go back to the literature from several decades back to the 1950s and 60s to identify resist chemistries that were rejected by the semiconductor industry to identify the gratone resist chemistries that work for us, that have the desired UV sensitivity linear dose response, and the target edge selectivity to achieve the variable edge depth. This was a non-trivial multivariate co-optimization that involved novel materials and process research. You can learn more about the detailed chemistries in our previous publication in the SPI Advanced Lithography in 2022. The final key invention was that with the overcoats. Typical high-efficiency grating designs demands overcoats that have no ripples over gratings and over the whole waveguide area. So having a constant thickness over all the gratings, irrespective of their fill factor or their depth. So you can break this problem into two problems, the sub-problems. The first is eliminating the ripples, which over the gratings, which is a nanometer scale resist reflow requirement, overcoat reflow requirement for this overcoat material. However, having constant thickness over all the gratings, that's a millimeter scale transport problem. Now, we are talking about nanometer scale as well as millimeter scale transport problems. So for any chemical engineers in the audience, this is a fundamental transport phenomena issue that no material can achieve by itself. It is impossible. This required both material and process innovations. On the process side, it required us to use inkjet-based spatial material dispense based on the fill factor. So where you decide to dispense a certain volume of material based on what volume you are filling. And on the material side, it required us to engineer new material formulations that have the target refractive index, the target absorption, and the target reflow that enabled us to achieve the desired grating unit cell for Orion. Now, I touched upon a smidgen of key inventions that went into creating this beautiful looking silicon carbide wafer showing the waveguides. On a nanoscale, these gratings look beautiful. And these are one of the most sophisticated SRG grating-based waveguides in the world. Now, this is what made Orion a reality. The large field of view at the eyeglass form factor was the world's first immersive augmented reality glass and gave a glimpse to the future of the industry. The display is just one part of the innovation that went into the product. But this is probably one of the most sophisticated consumer devices ever made. You can learn more about the different components in the meta blog that I can attach in the comments later after the presentation is finished. Pictures don't do justice to the immersiveness of the field of view that you can experience with Orion with amazing image quality. The rainbow performance is, of course, awesome. That is orders of magnitude better than anything else that is available in the market at these field of views. And at least for me, for the first time in my career, trying different AR glasses, Orion made me appreciate and enjoy the display and the field of view without getting bothered by the see-through issues like rainbow or the glasses weight. Now, experiencing Orion gives you the feeling of peering into the future in a time machine. And I have a clip from the video that we had during the Orion launch that talks about the silicon carbide waveguides and the display innovations.
Looking at the culmination of decades of breakthrough inventions in nearly every field of computing. It's one of the hardest challenges the tech industry's ever attempted. See, Orion is a time machine. It'll let Meta live in the future as they build the next generation of AR experiences. Now, let me nerd out for a second because this is a technological marvel. The display isn't made of glass. It's made of silicon carbide, which delivers an unprecedented 70-degree field of view. That means Meta engineers figured out how to bend light beams in ways it does not like to bend.
So I would have not called it silicon carbide, it is silicon carbide. That's the only change that I would make. Now, looking back at what it took us to achieve, what we achieved for the silicon carbide waveguides for Orion, I would say this was our version of the moon landing. Exactly same as the Apollo program. It is very expensive, took a lot of resource investments, but while doing it, we invented a lot of different things. We started our AR program with the 3-plate 1.7 index class waveguides with then graduated into two-plate Index 2 based glass waveguides, and ended up with Orion with a single-plate silicon carbide waveguide. And during this journey, we invented many different technologies that you would be hearing from from my colleagues in various conferences and in various publications that we have, and also from the Meta blog on what other inventions we came up with during this journey. Similar to the moon landing, there are still a lot of areas that need improvement before this technology can become ubiquitous, and all of us own an Orion. The first key challenge for SRG waveguides that needs to be resolved is the display wall side leakage. Due to the non-zero diffraction efficiency of SRG gratings, in the complementary orders, when the display is on, some of the light leaks out in the direction towards the observer, as you can see in this image. As the displays get brighter, even a few percentage of leakage might be visible, which is distracting for the social eye contact that we are used to. And this is especially a big problem at large field of views. But interestingly here, the steep slant gratings that I talked about before, the 60-degree slant, they do have a dual benefit. You can see here in this simulation, they enable high display path efficiencies while simultaneously having low leakage path efficiencies, which results in low leakage. But this is not enough. As displays get brighter, more research is needed into inventing new modalities for leakage reduction for the SRG waveguides. The second key thing is the cost. Anyone in the audience who wears prescription glasses knows how expensive they are for a dumb piece of hardware. Now, when you add to it one of the most sophisticated displays and sensor suites, the cost needs a lot of attention, especially with the silicon carbide waveguides, which are some of the most expensive substrates in the planet. Increasing the substrate size for optical grade silicon carbide would be the first step, followed by optimized manufacturing approach that could further reduce down the cost. And no one company or no one research institution can solve this. And the whole industry and academia needs to come together to identify the paths by which the cost can go down for silicon carbide waveguides. A precedence for this exists in the semiconductor industry with extreme ultraviolet lithography, where the whole industry and academia came together to invent the extreme ultraviolet lithography and make it happen. Now, the final key challenge is that for truly being immersive and being all-day wearable, AR glasses will need to work both indoors and outdoors with a runtime of at least 12 to 14 hours before charge, which is what we typically expect from our smartphones today. In addition to the advent of AI assistants, so we have been hearing a lot about the AI assistants. And if anybody here saw the Super Bowl, you saw the Ray-Ban Metas with the AI assistant on how useful and fun it is to help you with your daily life. With those AI assistants, there is a continued pressure for reducing the power consumption for the display modules for the future. And this doesn't even consider the case where these AR glasses might replace your smartphones and hence also enable cellular connectivity or maybe satellite connectivity with the Starlink or the Project Kuiper. This all points towards that the display will have a much, much smaller pie of the energy budget that it can use. This, in our opinion, is truly the challenge for the future for AR display. Now, people replication waveguides, they have been the main workhorse for the AR display industry, and they are the fundamental, they are the mechanism, and they are the path by which we achieve the Orion glasses. But for this future modality, they have a major flaw. Due to the very nature of attentive expansion through pupil replication, it is highly inefficient. Because in the eye box, while the pupils are being replicated, multiple pupils are being replicated, your eyes are just capturing one pupil. So rest of the light is being wasted. A rough back of the envelope calculation will tell you that 1 out of 1,000 photons reach your eyes. from the waveguide. This is the problem for the future, in our opinion. We need a paradigm shift in the AR display system in the future if AR glasses are to be as commonplace as smartphones. And there is no other group, no other collection of individuals than the people who are here, gathered here to enable this, who can invent new architectures and components to break through this wall. And solving this challenge will need strong collaboration, both within the academia as well as with the industry to solve this problem. We are always open to new ideas and concepts and would love to hear if you have something. And with this, I'll conclude my talk with the acknowledgements. Making true immersive AR glasses is difficult, and the work that I presented are the contributions from many, many of my colleagues. And I would like to thank each and every one of them for their groundbreaking research over the past 8 years. It takes a village to do what we do. And thank you. This we should be good for questions.
Yeah, thank you, Nihar, for a wonderful talk. So we'll take any questions either here in the room or on Zoom. I don't think there was anything in the chat, but on Zoom, you can either unmute yourself or type anything in the chat, and we'll take the questions. So, yeah, Daniel.
Thank you, Nihar, for the talk. This was as engaging to listen to the second time around. I have a question about the slide where you were comparing the different refractive indices and the achievable field of view with a single plate. I presume that's based both on the field of view, but also on the wavelength range, on how many wavelengths you want the waveguide to support. Is that correct?
That is correct. Yeah.
Okay.
For
because for a
RGB
single wavelength, you can achieve larger field of view for.
That is correct. Yeah. Yeah.
Okay, great.
Absolutely.
Thanks.
Yeah.
Hello, this is Unique. Roland, how are you? Just a quick question. Can you discuss a little bit more your decision making around doing butterfly versus the cross grading?
Yep. So basically, the question is between butterfly grating architecture versus the
cross grading. Yeah, I guess because the L shape is, we know the trade-off there.
Yeah, I think if you look at so basically it was all based on the form factor and the efficiencies. If you look at the same PDK, the process design kit that you have available, and do an optimization for, let's say, a butterfly-based approach versus butterfly, in my mind, is kind of a multiple one-dimensional expansion. And then you do folded is a multiple one-dimensional expansion, and butterfly is the two-dimensional expansion and outcoupling. So if you compare both, you will find that what we found is that the butterfly could enable paths to much higher efficiencies without blowing up the form factor. If you allow the form factor to be as big as possible, then a larger folded will match the butterfly. But if you constrain the form factor, then butterfly beats the folded architecture. And we prioritize the form factor. So we had a specific shape and form factor that we had to meet to not be like goggles. We wanted them to feel like glasses.
So just a follow up to that. Oh, sorry, did I speak over Anis? Oh, okay. So when you say butterfly, you don't mean splitting the field of view in half and propagating two separate field of views, because
that's split folded. So butterfly is kind of, you have gratings on front side and back side, and they are just.
So it's two gratings functioning as a cross grating back to back. Yeah,
that's correct. Yeah, you could achieve the same thing with a two-dimensional grating also on just single side.
That makes sense. Okay, great. Thanks.
On Zoom from Barry, how long does it take to etch one waveguide? And also, are there any commercial tools that you use for ray tracing and optimizations?
How long does it take to etch? That I can't comment on it. But of course, if you look at what are the typical, how long does it take to do a typical etch step in semiconductor? It's usually, let's say, 6 to 7 wafers per hour. So I think that would be your reference on kind of figuring out what the industry would be working towards. Then the second question was
The question was, are there any commercial tools that you use for ray tracing and optimizations?
There are commercial tools, but our tools are designed internally in order to kind of massively scale into our data center infrastructure. We can't use commercial tools in our data center infrastructure.
Are there any other questions here in the room?
One more question. So when you etch your gridding, so are you able to quantify like the defects? Because it's really challenging that, 60-degree kind of thing, 45 to 60 degree. So you're able to quantify the defects and then kind of understand the impact on the optical performance?
Yep. So I think it depends on kind of what you mean by defects. The beauty of visible light is that it's impervious to what in semiconductor would be a killer defect for an electrical circuit. So yes, we do quantify the defects. We don't see it as a challenge for this technology.
Okay, thank you.
Any additional questions on Zoom? One more in the room, right?
This is, I guess, a user question. Looking at how, I guess, fragile are these surfaces and lenses to water, oil, if you smear a finger or a Kleenex rather than a lens wipe. So it seems, especially with a 45 to 60 degree angle, that sort of, if you will, overhang. I just imagine, if you squeezed that surface, you could, I don't know, snap those heavily slanted surface angles. So how durable or fragile are the Orion lenses?
That's a good question. So if you look at how typically the AR glass implementation is, the waveguide is never exposed to the user. They have what is called the push-pull lenses because of the very nature of closed case face and people replication, the image is at infinity. You need to pull it down to what we call the Percival's zone of comfort, which is around 1 meter, 0.7 to 1 meter. So there is push-pull lenses, and the waveguide is sandwiched between that. So you never kind of, other than the factory, no one else touches the waveguide usually.
Any other questions? There are no further questions. Let's thank our speaker again.
Yeah, thank you.
Thank you. Thanks for the invitation to speak.
So if you'd like to continue following their work, the contact info is in the Zoom chat. Please check out the rest of the Voice of XR speaker series. And also you can check out the recordings of previous talks on the Studio X website. Links are all in the chat. Thank you very much for joining us today. And thank you, Nihar, for a wonderful talk.
Absolutely.
Wonderful.
Thanks.